Okay, so let us start today's session. Hello and welcome to this NPTEL TA session on the course Transport Phenomena. And today is week 6, and we will be discussing uh, some concepts, new concepts today, and also looking into some of the problems. So, first, we'll look into some of the concepts related to uh, turbulent flow. Okay. And some velocity distributions, some concepts that are used in turbulent flow that we will be studying. Like till now, we have whatever we have studied is mostly based on laminar flow problems. We have seen differential equations describing laminar flow and also understood that. But those equations are pretty much, straightforward. But can we apply those equations in the case of turbulent flow? Uh, Let us take one example. Simple example was we saw flow through a pipe. We saw that velocity in a particular direction is a function of how it changes. Let's say the z velocity changes with respect to r, a particular variable. But in turbulent flow, we probably cannot say that because this velocity can be a function of many variables. So the first idea that we get is this turbulent flow is a chaotic kind of flow, right? So let us start with some comparison between laminar and turbulent flow. Okay. So let us see how both the flows can be different. Okay. So we'll consider one example of flow in a conduit. Okay. Conduit, it's like a pipe flow. We'll start with flow through a conduit and we'll see different cases. Why I'm considering this? Because uh, similar situations we have already studied in laminar flow, flow through a pipe and flow over a flat plate. All these things we have already developed our concept for laminar flow. So we will see how these things can be different in case of turbulent flow. So in a conduit, let's say circular conduit, or we can say circular tube, we have. So we know that the velocity distribution, we can write something like this. If you remember, Vz by Vz max is equal to 1 minus R by R square. Right? And if we take the average velocity by Vz max, that will come out to be 1 by 2. Okay. And these are expressions that are obtained for laminar flow case, if you remember. So Reynolds number is less than to 1 0, 0. That is laminar. Similarly, pressure drop expressions also we have developed, like let's say P0 minus equal to. So this is the pressure difference. But for turbulent flow, the velocity is fluctuating with time at each point in the tube. Like, say, if you remember, this is kind of a parabolic profile. But for turbulent flow, we will not be having such a smooth profile. Rather, it will be a fluctuating profile. And therefore, how do we obtain expression for such velocity? So for that purpose, we measure something called a time smooth velocity. Okay, let me write. There's something called that means some average velocity over a period of time. Okay, that means velocity averaged over several seconds. Let me write. Okay. Now, what is this time smooth velocity? We'll look into this just a little bit later. But now just consider that it is some kind of a average smooth average velocity that we are considering. Okay. So it's an average over time. Remember that it is a time smooth velocity. So it's a averaged over time. So it is still remains now, since it is averaged over time, it only remains now as a function of one particular coordinate. Like, say, for example, how we obtained here. But here we know that it was not fluctuating with respect to time. So we can directly write this expression. But since now it is fluctuating, we have considered a time smooth velocity. And now with this smooth velocity, we can write expressions for velocity distributions. So let me write. So for this turbulent flow, we can write Vz bar. I'm writing Vz bar for time smooth velocity divided by Vz bar max. And this is approximately equal to 1 minus r by capital R to the power of 1 by 7. And similarly, we can also write Vz bar average value, okay, divided by Vz max is equal to, not equal to, roughly equal to 4 by 5. So this is for high Reynolds number, that is Reynolds number in between 10 to the power 4 to 10 to the power of 5. So this is, you know, what is this? This is turbulent flow. Okay. So you can see clearly they are quite different. These expressions are quite different for both laminar and turbulent flow. So let us plot these two expressions and try to see what is the difference. Okay. So how they are different, and you can get a real feel about what makes them come very different. Let's say. So here I'm plotting R by R. Okay. And here let me plot VZ bar by VZ bar max. Since this is a ratio, this will change from 0 to 1. And let's say this is kind of center. So this will be 1 and this will be 1. So if we plot the parabolic profile, this will be something like this. Right? Something like this. The parabolic profile. Let's say I'm writing this is for laminar flow. You can see it is a smooth parabolic profile. And this I'm deleting. Let me bring this here. It will be better. Okay. And if we plot the same for the turbulent flow, it will be something like this. Okay. So this is for turbulent flow. And this point is, as you know, is the tube center. This is tube center. Okay. And these one will represent the tube walls. So you can see how the two distributions are quite different. Okay. So you can see both laminar and turbulent flow can be quite different. So I'll do one thing. I'll just take this image and fit it here. So it will be. I think now it is better. Yeah. So I think you can understand how different can be both laminar and turbulent flow. Just like how this velocity distribution changed, this pressure distribution will also be different for laminar flow over the same range. This range, this pressure distribution will also be changing. So let me write it so it will be better. So this is P0 minus PL will roughly be equal to 0.0198 times of 2 by pi 7 by 4. So mu to the power of 1 by 4 L rho r to the power of 19 by 4 times of w to the power of 7 by 4 for same range of Reynolds number. Now for turbulent flow, this pressure drop for in case of turbulent flow will be higher than that obtained from the laminar flow, and this is because some of the energy that is provided for the fluid to flow will be lost due to the or supplied to the supplied pressure energy will be used by some of the eddies that are generated in the fluid, and therefore we will have a stronger dependence of the pressure drop on the mass flow rate for turbulent flow. And as I said, this is for the energy has to be supplied to maintain the eddy motion in the fluid. So that is the basic idea. So this is one example of a circular tube. Similarly, we can look for non-circular tubes as well. We can get similar expressions for non-circular tube. Let me do one such example. So if we have a triangular tube, triangular duct, we can see the velocity will be in z direction, that is into the plane of the paper, and it will be in contact with three walls. But if you see, in this case, because of the presence of these edges, we will be having eddies will be developing. And how these eddies will look like, let me draw. Let's say I'm dividing into three parts. So here we will be, these eddies will be developing something like this. Okay. Similarly, eddies will be generated here and as well as here. And the direction of these eddies will be, like this. So since it is, near the wall, it will be at rest, and near the center, the fluid velocity will be maximum. So the flow will be something like this. Okay, from center to outside, because from the center the fluid will try to push the nearby fluid, so it will be something like this. Similarly, here also it will be like this and like this. Okay. Similarly, we have studied about flat plates. If you remember, the last class also we did a problem on flat plate. So we saw that when we have a boundary layer formation on two sides of the flat plate, the drag expression for drag force can be written something like this. If you remember from the last class, we have exactly obtained at this expression. You can go through the notes also. Okay. And this is for Reynolds number from 0 to 5 into 10 to the power 5, which is the critical Reynolds number for transition from laminar to turbulent flow for flow over a flat plate. Okay, but for turbulent flow, the dependence of the geometrical and physical properties are quite different than this expression. So it is something like this. So it is around 0.74, and we have fifth root of rho to the power 4 mu times of L to the power 4 V infinity to the power 9. So you can see that it is quite different from this. So it is from 5 into 10 to the power 5 to 10 to the power 7. So quite different expressions for laminar and turbulent flow. So this is 5 by 2, power of 5 by 2. Okay. But one thing from all these expressions, what we can see is to maintain the same flow in turbulent flow, especially in turbulent flow, we need higher energy, either in circular tube or in non-circular tube or in flat plate. So this is something that I may write as a note, that in turbulent flow, we require extra energy because more energy is has to be supplied to maintain the eddy motion in the fluid. So this is something that is a general thing that we can conclude from our observation till now. So we can understand from this that the turbulent flow can be quite different from the laminar flow. And but one general thing we can see is that we require some higher energy to maintain flow in case of a turbulent flow. Okay. Okay. Now let us go back to more mathematical sense. See, we have considered something called time smooth velocity. Okay. So now let us try to see what is time smooth velocity and how we can modify our already existing equations for this time smooth velocity. Okay. So let's see. Let us first consider a turbulent flow in a tube. That is the most simple case with a constant pressure gradient that is imposed on the flow. If, say, at one point in the fluid, we observe one component of the velocity as a function of time, say some at some random point, we see how the velocity is changing with respect to time, and we see that it is fluctuating in a chaotic fashion. Let me draw, it will be better. Okay. So let's see, this is fluctuating something like this. Some chaotic fashion, it is fluctuating. Okay, so this is the velocity and this is the time. And the fluctuations are very irregular. So what we can say is, let us consider that there is some mean velocity. Okay, let me draw some kind of a mean velocity like this. So this is, let's say, v. Let us consider this as vz. So vz bar, and we have fluctuating components. That is, uh, let us define something like this. Let's say this. And this is actual velocity we know. So we have vz, which is a function of time, definitely. Okay. And we have some vz bar, that is some time averaged velocity. Therefore, we can write that the velocity vz, which is a function of time, is equal to, at any point, is equal to the value of the average velocity plus some fluctuating component, that is vz prime. Okay. So such type of notation is called Reynolds decomposition. Reynolds decomposition. Now, how do we obtain this average velocity with respect to time? We can do that by integrating this Vz, let's say ds and ds, okay, in some time frame, that is t minus, let's say, half t0, and t plus half t0, some time frame t1 to t2. So this is average over some time divided by the total time of observation. Now let me uh, tell you one thing. You can see that here we have considered Vz bar, which is not a function of time. That means we have taken a time average velocity, but this time average velocity Vz bar does not depend upon time. But for some cases, this Vz bar can also depend on the time. So how can we plot it? So it will be better if I just plot it and show you. So this is Vz and this is time. And let's say I'm drawing something like this. Okay. So here you can see if we draw some average value, it will be something like this. So this is Vz bar, which is a function of time. Okay. So here Vz is actually a function of time. And this term that we have now, this Vz bar, is nothing but the time smooth velocity. Okay. But for our cases, we will be considering this, that it is independent of time. For our cases, we will see that it is independent of time. This time smooth velocity is independent of time. Now, just like how we say steady flow, if you remember, so if any parameters like velocity, when it is independent of, which does not change with respect to time, we call it steady state, or unsteady state if it is dependent on time. Similarly, if Vz bar is dependent on time or not, we call it steadily driven turbulent flow. Okay, if it is independent of time. And same is the case for pressure also. Okay. Okay. Now, before moving into next thing, let us consider some important thing here. This time t naught that we have, okay, this should be large enough so that, like, should be large enough as comparison to the time scale of the fluctuations. Time scale of fluctuations, so that we can get a smooth VZ bar. Okay, so that we can get a smooth VZ bar, but should be smaller than the application of any kind of external driving force like pressure. Okay, like let's say for example we are applying it for 5 seconds, so that this t naught should not be as large as 5 seconds. Okay. Okay. Now let us see some properties that we can derive from this time smooth velocity. Some observations we can say. Now this is the fluctuating component, that is Vz prime. So what will be the average value of this fluctuating component? So we can see the average value of this fluctuating component can be written as 1 by T0, correct? Integration of T minus 1 by 2 times of T0 to T plus 1 by 2 times of T0 times of Vz prime, right? ds. Now this Vz prime we can write this Vz prime I can write Vz minus Vz bar times of ds. So this is equal to, we can again write individually, we can write so this will be Vz times of ds, right? Plus we will be having this will be Vz bar. But you know, Vz bar is not a function of time as such. And this particular expression that we have here, this thing, what is this? This is nothing but Vz bar. I can write this as Vz bar, correct? So this will be equal to, we can write Vz bar plus here also Vz bar by T0 integration of this particular term. Which is this minus this. Okay. No, sorry, this will be minus sign, right? This will be minus sign. So we can write this as this is equal to Vz bar minus Vz bar by T0. We have T plus 1 by 2 T0 minus T plus 1 by 2 times of T0. So this will be cancelled out. This will be T0, T0, T0 will cancel out. So this will come out to be 0. So what we obtained is this Vz prime bar is equal to 0. That means over the average value of this fluctuating component over this time frame is actually 0. There are many other observations that we can write. Let me write. One is Vz bar, which is the average time smooth velocity. And if we take the average again of that, it will be nothing but same as that of Vz bar. Okay. Similarly, if we take Vz bar, that is the time smooth velocity, and then multiply it with the fluctuating component, that is Vz prime, and then take the average, then it will be equal to 0. Because this term will be constant, and when we take integration, when we take the average value, it will come out, and therefore we will be having 0. Similarly, if we take the derivative of, let's say Vz, and take the average value, it will be same as that of Vz bar. Okay. So these are some of the important relations. Again, let me write one thing. So this is for any coordinate system that we have. Also with respect to time also, if you do it, then also you will be having. So these are some of the observations that we can derive from this definition. One I have shown you, first one, rest of the you can do it by your own also. However, there is something that we have to keep in mind, that this quantity, that is Vz prime square average, is not equal to 0. So this is something to note. So this you can check by yourself also. But when we take product of fluctuations, then that is not equal to zero. Okay, because we have two terms that are on an average it becomes zero, but when we take the product, sometimes it may get amplified also, and it will not be zero on an average. So that you have to keep in mind. There is in fact one ratio, something defined like this. Let's say vz prime square, and the square root of this term whole divided by the vz bar average value. Okay, and this is generally taken as a measure of the magnitude of the turbulent fluctuation. And also may be called as intensity of turbulence. Okay, so remember this thing that when we have product of fluctuations, then that is not equal to zero. Similarly, we can also write vx prime times of vy prime, and if we take the average, then that is also not equal to zero. So that you have to keep in mind. Okay. So uh, this statement, what it tells us that the fluctuations in the x and y directions are actually dependent. Okay, the fluctuations in x direction is not independent from the y direction. Okay, so now since we have defined what is this time smooth velocity and everything, let us move forward and substitute this into the equation of change that we already have, like continuity equation. We have Navier-Stokes equation. So let's see how we can modify those equations to incorporate these terms. So let us start with the continuity equation. So we can write, let's say, dou by dou x times of, instead of Vx, we can write, let me write it. We can write Vx bar plus Vx prime. And this is equal to 0. Similarly, we can start with the momentum equation. Uh, okay, I think now it is clear what I have written here. Similarly, you can write the y and z component of this Navier-Stokes equation. Now let us time smooth these equations. Okay, that is time smooth these equations. So let's start with this one. So if you time smooth this equation, you see uh, uh, integration over this term. This will be the average of the average. If we do that, then that will be nothing but the average value that we know. So average of the average will be the average value, and average of this fluctuating component, that is Vx prime bar, will be equal to 0. So if we time smooth these expressions, all these fluctuating components will go out. So what we will be left out with is this will be equal to 0. So this is by time smoothing the first expression. Similarly, if we time smooth the second equations, you see this in this term will go away to be 0. This term will remain. So let me write. So this term will go away, correct? And similarly, fluctuating component p prime will go away. Okay. Now, if we see this side, this term will go away for sure, and this term will remain. But this term we have to see what we can do. So let me write first the this major part, and then I'll see what we'll do with this. Okay. So if I write, we have dou by dou t of rho Vx bar, that will be equal to minus times of dou by dou x of p bar plus mu times of del square times of Vx bar plus we have rho times of gx plus we have these terms. Now we can just expand one of the term and we'll see what happens. Okay. Okay. So I'll write. I'm for now. I'm not writing what will come after this. So let us simplify and then we'll put it here. So let me do with, let's say, this one, and we'll see what we are ending up with, and then we can substitute it. So let us take the product. So this will be equal to dou by dou z times of rho. So we have Vz bar Vx bar plus Vz bar times of Vx prime plus Vz prime times of Vx bar plus we have Vz prime Vx prime. So if we take the time average of this thing, you see this is average value. So this will still be there. These are two fluctuating components. I have mentioned that this will not be equal to 0. right? So this will be there, and here we will be getting average of this. So if you see this expression, this will be 0. So these terms will go away. So this term will go away, and this term will also be going away. Okay. So what we will be left out with is, if we take the time average of this, we will be left out with is dou by dou z of the rho times of the two product average, that is Vz Vx bar, plus the product of two fluctuating components and that time average of that. Okay. So let us substitute that here. So I'm just writing it as side note. So let me write it something like this. So this is kind of a side note. Okay. So now if we add these here, what we will be ending up with is, so we have minus term is there. So we're having minus. So we see there are two terms, one with the product of average. So we have dou by dou z of rho vx bar plus, sorry, this is dou by dou x by dou y of rho vy bar vx bar plus dou by dou z of rho vz bar vx bar. Correct? Minus, again we will be having terms that will be related to these fluctuating components. So we have dou by dou x of rho vz vx prime bar okay. I think it is clear. So these are the time smooth expression for equation of motion. So what we see is that this continuity equation is same as that we already previously have, only Vx is changed by V bar, Vy by V bar, something like this. Okay. The equation of motion has V bar and P bar component, where we previously had V and P. In addition, there appear to be dashed underlined terms which describes the momentum transport associated with the turbulent fluctuations. So this term, particularly this extra term that we have. Okay, so which is nothing but uh, so this additional term that describe the momentum transport associated with turbulent fluctuations. So you can also write these terms in terms of, you know, uh, like turbulent momentum flux tensor, like in terms of turbulent momentum flux tensor. So in terms of that also you can write like say tau x bar, which is obviously function of t, will be equal to rho times of vx prime vx prime and bar. Similarly, tau yx will be equal to rho times of vx prime vy prime average, and similarly tau zx. Okay, so you can write also in terms of this momentum flux tensors also. And all these quantities that we have here, these are also very popularly known as Reynolds stresses. Okay, these are also popularly known as. Okay, so just like how we named them as turbulent momentum flux tensors, we can also introduce a symbol for time smooth viscous momentum. So these terms we can also write, let's say tau bar of V. So this is for viscous. Okay, similarly XX, YX and ZX. So which will have the same form that we already have previously, because these are all very similar to what we have for viscous flow. This is the additional term that we have. Therefore, all the equations like the continuity equations, the momentum equation in vector form, they will reduce to very simple form. Let me write. Let me take another. Let me take this one. So it will be easy. So the equation of change we can write del dot v bar is equal to 0. Mhm. Final. Let me write final equation of change. So one is this. That is from here we have this one. Okay. Now if you see, if I just this term, if I subtract it from here, you see we will be having all the fluctuating components as well. So we will have another term, something like this, del dot v prime is equal to 0. Okay. And we have the momentum equation, that is dou by dou t of rho times of v bar, that will be equal to minus times of divergence of p bar minus times of. Now what we will be having, if you see, that is this term, correct? So that is of rho v bar times of v bar, and this will be a tensor minus times of we have the viscous term plus the terms related to the Reynolds stresses. And this is again a tensor plus rho g. So these are the final forms that we have. So we can see that once we are considering this time smooth velocity, we can use same expressions for continuity, but instead of velocity, we have to substitute the time smooth velocity value. And similarly, for equation of change, time smooth velocity can be replaced with time smooth velocity, pressure with time smooth pressure. And instead of the stress, we have to add two terms, that is for one for the viscous momentum flux and one for the uh, this fluctuation that is coming from the turbulent flow. Now, once we are developed with all these things, we are still having one of the major problem to solve this. And what is that? That is these Reynolds stresses that we have above that are related to the velocity, but you can see these Reynolds stresses are not related to velocity gradients directly, but rather they are complicated functions of position and turbulence intensity. Therefore, we cannot solve these expressions directly. So we have to resort to other forms like empirical solutions and everything. Okay. Because we cannot solve these stresses or these Reynolds stresses directly. Okay. Okay. Now let us move forward and see the time smooth velocity profile near a wall. Okay. So let us see. So uh, why I'm taking this example is, you see, before going into the empirical relation for this Reynolds stresses, let us. It is first important to see that there are some cases that are still there where we do not need these empirical relations. We can directly obtain solutions for this, and let us see such problems. Okay. let me draw first and then we'll see. So this is the velocity distribution, you know that. Just draw. So there will be three layers. There are three layers that are very close to this wall. So this is flow near a flat surface. Okay. So you can see there are four regions actually. To be true, four regions. One is this one, that is region one. One is this one, this is region two. One is this one, that is region three, and one is region four. So there are four regions that we can identify. So the region one is the viscous sublayer. That means very close to the wall, even in turbulent flow, very close to the wall, we have a very thin layer that is viscous in nature, where viscosity plays a key role. So this is the viscous sublayer. Then we have a buffer layer where the transition occurs between viscous and inertial sublayers. And then we have a inertial sublayer. This is the inertial sublayer. Okay. So at the beginning of the main turbulent stream, the here actually viscosity plays a minor role. It is there, but it will play a minor role. And the fourth is the main turbulent stream. That is, this is the main. Okay, for now, let us consider, let us consider that the time smooth shear stress acting on the wall at y is equal to 0 be called tau 0. That is here. Okay, so this is same as we can if we write tau yx bar because time smooth at y is equal to 0. Same thing. Okay. Then the shear stress in the inertial sublayer, this inertial sublayer will not be very different from the value of tau naught because it is a very small layer, right? Now, on what quantities will the time smooth velocity gradient? So, this term, if we write, we have a velocity gradient that is dv x bar by dy. On what quantities this velocity gradient will depend upon? Uh, like beyond this, beyond this viscous sublayer, from this inertial sublayer, if we see, so on what quantities will this velocity gradient will depend? So it will not depend on the viscosity because there is no influence of viscosity once we go beyond inertial sublayer that we have already considered. Okay, viscosity is primarily dominant near the viscous sublayer, and here it should mostly depend on the velocity fluctuations or eddy motions, we can say. But it can depend upon properties like density of the fluid. Okay, it can depend upon like tau naught. Also, it can depend, and also how far from the surface is we are calculating this velocity gradient. That also it will depend. Correct. So if we see, this is a velocity gradient. So it has a unit of 1 by s second. So if we rearrange these terms, we will be ending up only with one quantity, that is tau 0 by rho square root times of 1 by y. This is the only term from these three quantity that will end up with the same dimension. And therefore, we can write this dv x bar by dy is equal to, uh, will be related to tau 0 by rho times of 1 by y and square root of this, but there will be one some constant, let be 1 by k, but this k is a dimensionless constant. This tau 0 by rho and this square root of this has the dimension of a velocity. If we check, it will have a dimension of velocity, and therefore it is also called the friction velocity, and is given a special symbol called v star. Okay, so if we do that, we can write this dou vx bar by dy is equal to 1 by k v star times of 1 by y. So if we integrate this, we will be having Vx bar is equal to V star by K times of ln of y plus some constant of integration, let's say lambda prime. So if we write in terms of dimensionless parameters, you can see we can write this as Vx bar by V star, because both are, and this will be 1 by K. And here we have to add something that will be, you know, from known quantity or from properties of fluid. So if you see, uh, mu by rho, that is kinematic viscosity, is nothing but meter square per second. And if we have V star, that is meter per second. So if we take nu by V star, that will be equal to meters. So here we have Y. So we can divide by nu and V star, which are all constants or things we can already obtain. Okay. And the rest of the terms we can incorporate here, that is lambda. And this is the expression that we have. And the constants that we have here, that is K and lambda, they were obtained experimentally. And it was obtained that the reasonable values of K is around zero point 0.4 and lambda is equal to 5.5. Okay, and this value was uh, holding good for y v star by nu value greater than 30. Okay, and this expression, this is called, let me write, this is a very long name. So this is called the Karman Prandtl universal logarithmic velocity distribution. And later many experiments were done, and it was shown that this expression was only moderately satisfying, or it was only, you know, moderately explaining the experimental data somewhat beyond the inertial sublayer. Therefore many modifications were also done to into this. Let me write. So it was shown that this k and lambda, these were not exactly constant values, but varies in some ranges. Like varies from zero point 0.4 to 0.44, lambda from 5 to 6.3, and many such reports were there. So these were not particularly constants. Okay, later it was found out experimentally. Although it is well, it can well explain the velocity, time smooth velocity beyond the inertial sublayer. But more modifications when people did, they found out. So later it was also suggested that this this thing that we obtain here, this one, later it was suggested that the right side of the equation should be multiplied by some functions of Reynolds number, because Reynolds number is also one of the parameter that defines turbulent flow. And also this y that we have, it should be also raised to some powers involving Reynolds number, and many such arguments were proposed by different researchers. Okay, so with that modifications, it turned out that this was one of the modification that was proposed. Let me write so that you can get a feel of what is that. Let's see, vx by dy, this is equal to v star by y, so b0 plus b1 by log of Reynolds number. So we see there are some terms that are multiplied with Reynolds number, and we have y v star by nu times of beta 1 by ln of Reynolds. So you can see that there is some powers raised to Reynolds number, y power raised to Reynolds number, some product of Reynolds number, where this b0 was root 3 by 2, and this b1, these are some experimentally they have obtained that these can be some of the modifications we can do. And beta 1 is equal to 3 by 2. And once we got this, you can again integrate how we previously did that. You can integrate that, and if you integrate this expression, you will get something like this: vx bar by v star is equal to 1 by root 3 ln of re plus 5 by 2 so y v star by nu equal to the power of 3 by 2 times of ln re. And this was famously known as the Baron Blatt, Baron Blatt Curin universal velocity distribution. And this distribution could explain these inertial sublayer and turbulent stream. in a much more better way than this expression could able to do. Okay. So this was mostly for what we say for the inertial sublayer. Now, what about the viscous sublayer part? Okay. What about the viscous sublayer part? So that also we have another theory. Let us see. So for the viscous sublayer part, since viscous sublayer is very close to the actual surface, so we can write a Taylor series expansion for velocity distribution. So for the velocity part, let us write a Taylor series expansion. So and we can write this as a function of, so we can write Now to evaluate the terms in this series, we need the expression for the time smooth shear stress in the vicinity of the wall. Now for the special case of steadily driven flow in a slit of thickness 2b, the shear stress will be of the form something like this. That is the viscous plus will be equal to something like minus tau 0 times of 1 minus y by b. Okay. And if you remember what are these terms, this is the viscous part. So we can write mu times of dou Vx bar by dou y minus this is the rho times of Vx prime Vy prime bar. This will be equal to tau 0 times of 1 minus y by b. Okay. Okay. So this is at y equal to 0. So you see this term will be equal to 0 because of no slip, because this is at y equal to 0. And this coefficient that we have, this one, this we can obtain from this expression, right? So how we can do that? You see, uh, we can write dou times of Vx bar by dou y at y equal to 0. Now at y equal to 0, all these fluctuating components will also be 0. So and this side, this y equal to will be 0. So we will be having tau 0. Thus we have dou Vx bar by dou y at y equal to 0 is nothing but tau naught by mu, which we can substitute here. Similarly, the third term, this one, involves the second derivative, which may be obtained by differentiating this term with respect to y and then setting y equal to 0. Correct? So let me write and try this. So this is mu times of del Vx bar by del y. This will be equal to rho times of Vx prime Vy prime whole bar plus we have tau naught 1 minus y by v, right? And we differentiate this, or just let me do this by mu by mu. Okay, so dou vx bar by dou y square. So this will be equal to rho by mu times of vx bar dou y plus this will be minus tau 0 by mu times of b. And if we again set y equal to 0, that is dou square times of vx bar by dou y square, and set y equal to 0, then this entire term will be 0. So we are left out with minus tau 0 by mu times of b. Now again, for this term, we have to take the derivative of this expression. So it will be 0. Okay, because if you see, this term will go to 0 if we differentiate it. Only the fluctuating terms will start to repeat after that. Okay. Okay. So if we write this, we can see, let us start to write it. What we'll see, we have Vx bar, which is a function of y, but I'm not writing it now. That will be equal to tau naught tau 0 by mu. So we have times of y. Then we have plus 1 by 2 times of minus tau 0 by mu times of b times of y square, plus some terms whatever we have. Now we can write it in terms of dimensionless parameters as well. So we can, let me write here this tau 0 by, here I can write mu by rho times of rho, and here y also, if you remember how we dimensionalize it, we have v star by nu, right? So this is new already we have. So I'm taking it here. So this is new. And this tau 0 by rho that we have, if you remember, what is that? We have v star. Okay. So that will be v star square. So here it will be V star square, but I'm taking one V star this side. So Vx bar by V star. So first term will be y V star by nu, and all other terms that we will be having will be in the form of these dimensionless parameters. And this is for y V star by nu less than 5. From 0 to 5 actually better. So for today we'll discuss this much only. So we'll meet you again next time, next week, and we'll discuss few more concepts. Okay. And so till then, thank you.